Welcome to DAR Tutors. Today we're covering essential concepts for IB mathematics, specifically box and whisker diagrams, outliers, parallel box plots, and cumulative frequency graphs. We will begin with box and whisker diagrams. By the end of this section, you will be able to construct and interpret these plots using the 5-number summary. A box and whisker diagram, or box plot for short, is a visual tool that summarizes a dataset using 5 key statistics. These 5 values are known as the 5-number summary. Let's break down what each of these means. The minimum and maximum values are simply the smallest and largest numbers in the dataset. The median, or Q2, is the middle value when the data is ordered, dividing the set into 2 halves. The median Q2 is the 50th percentile. This means half the data values are below it and half are above it. The lower quartile, Q1, is the median of the lower half of the data, marking the 25th percentile. Similarly, the upper quartile, Q3, is the median of the upper half, the 75th percentile. Now let's see what a box plot looks like and how these values are represented. A box plot is drawn on a number line. It consists of a rectangle, or box, and 2 lines extending from it called whiskers. The box itself extends from Q1 to Q3. This central box represents the middle 50% of the data. A vertical line inside the box marks the median Q2. The whiskers extend outwards to the minimum and maximum values. This structure provides a clear picture of the center and spread of your data. The central box contains half the data points, and each whisker contains a quarter. Let's work through an example to solidify this. We'll use the data set provided in your notes. 8, 2, 3, 9, 6, 5, 3, 2, 2, 6, 2, 5, 4, 5, 5, 6. The very first step is always to order the data from smallest to largest. Ordering our data gives us 2, 2, 2, 2, 3, 3, 4, 5, 5, 5, 5, 6, 6, 6, 8, 9. We have 16 data values in total. Now we can find our 5-number summary. First, the minimum value is the smallest number, which is 2. The maximum value is the largest, which is 9. Next, the median, Q2. Since we have an even number of data points, 16, the median is the average of the 2 middle values. The middle 2 positions are 16.2 equals 8 and 16.2 plus 1 equals 9. The 8th value is 5 and the 9th value is 5, so the median is 5 plus 5 divided by 2, which equals 5. Now for the quartiles. Q1 is the median of the lower half of the data, which contains the first 8 values. The lower half is 2, 2, 2, 2, 3, 3, 4, 5. The median of these 8 values is the average of the 4th and 5th values, which are 2 and 3. So Q1 is 2 plus 3 divided by 2, giving us 2.5. Similarly, Q3 is the median of the upper half, which consists of the last 8 values. The upper half is 5, 5, 6, 6, 6, 8, 9, with the first 5 being the 9th value of the original set. The median of this half is the average of the 4th and 5th values, which are 5 and 6, so Q3 is 5 plus 6 divided by 2, which is 5.5. So our 5-number summary is minimum 2, Q1 2.5, median 5, Q3 5.5, and maximum 9. Now let's draw the box plot. We start with a number line that covers our data range. We'll mark the minimum at 2, Q1 at 2.5, the median at 5, Q3 at 5.5, and the maximum at 9. Then we draw the box from 2.5 to 5.5, the line for the median at 5, and the whiskers from 2 to 2.5 and from 5.5 to 9. We can also calculate the range and interquartile range. The range is the difference between the maximum and minimum, which is 9 minus 2, or 7. The interquartile range, or IQR, is the difference between Q3 and Q1, which is 5.5 minus 2.5, or 3. This IQR gives us the spread of the middle 50% of our data. You have now successfully constructed a box plot and calculated its key statistics. Next, let's learn how to interpret the shape of a distribution from its box plot. This allows us to make inferences about the data without needing the raw numbers. We will focus on 3 types of distributions: symmetric, positively skewed, and negatively skewed. First, let's consider a symmetric distribution. In a symmetric distribution, the data values are distributed evenly around the mean. This often results in a bell-shaped histogram. A box plot for symmetric data will be symmetric. This means the median line will be in the exact center of the box. Both whiskers, on the left and right, will have the same length. This tells us the data is balanced on both sides. Now let's look at what happens when the data is not symmetric. When a distribution is not symmetric, we say it is skewed. There are two types of skewness. A positively skewed distribution has a long tail extending to the right. This means there are a few unusually large values, or outliers, pulling the mean up. In a box plot for positively skewed data, you'll see two key features. The right whisker will be significantly longer than the left whisker, indicating the spread of those higher values. Additionally, the median line inside the box will be closer to the left edge, Q1. This shift in the median's position within the box is a strong indicator of positive skew. Conversely, a negatively skewed distribution has a long tail extending to the left. This is caused by a few unusually small values pulling the mean down. A negatively skewed box plot will show the opposite pattern of a positively skewed one. The left whisker will be longer, reflecting the presence of lower values. The median line will be closer to the right edge of the box, Q3. By observing these simple visual cues, you can quickly describe the overall shape of a dataset's distribution. While box plots are useful, a formal method is needed to identify extreme values, which we call outliers. By the end of this section, you will be able to apply the formal test for outliers. An outlier is an extraordinary data point that lies an abnormal distance from other values in the dataset. Simply looking at the data can be misleading. We need a consistent mathematical rule. This rule is based on the interquartile range, or IQR. The IQR, as you remember, is the range of the middle 50% of the data. The test for outliers uses boundaries set 1.5 times the IQR above Q3 and below Q1. Here are the formulas. The upper boundary is Q3 plus 1.5 times the IQR. Any data value larger than this is an outlier. The lower boundary is Q1 minus 1.5 times the IQR. Any data value smaller than this is an outlier. Now, how does this affect our box plot? If an outlier exists, the whiskers are no longer drawn to the absolute minimum and maximum. Instead, each whisker is drawn to the last data value that is not an outlier. Outliers themselves are marked on the plot with an asterisk. Let's apply this to an example. Consider the data set you have with the 5-number summary. Minimum 1, Q1, 6.5, median 8, Q3 10, and maximum 16. First, we need the IQR. The IQR is Q3 minus Q1, which is 10 minus 6.5, giving us 3.5. Next, let's calculate the boundaries. The upper boundary is 10 plus 1.5 times 3.5, which is 10 plus 5.25, giving 15.25. The lower boundary is 6.5 minus 1.5 times 3.5, which is 6.5 minus 5.25, giving 1.25. Now we compare our data points to these boundaries. Looking at our ordered data, the smallest value is 1, which is less than our lower boundary of 1.25. So 1 is an outlier. The largest value is 16, which is greater than our upper boundary of 15.25, so 16 is also an outlier. Finally, we draw the modified box plot. We mark the outliers 1 and 16 with asterisks. The box remains the same. But now, the lower whisker will extend to the smallest value that is not an outlier, which is 3. The upper whisker will extend to the largest value that is not an outlier, which is 14. Now that we understand how to handle single data sets, let's explore how to compare two or more sets. By the end of this section, you will be able to construct and interpret parallel box plots to compare distributions. Parallel box and whisker diagrams are a powerful tool for visual comparison of two or more distributions. The process is simple. You create a separate box plot for each dataset and you stack them, aligned along a single common number line. Let's work with the hospital drug trial example from your notes. We want to compare the effectiveness of an old drug and a new drug. First, we need to calculate the 5-number summary for each dataset. For the old drug, the times range from a minimum of 5 seconds to a maximum of 21 seconds. The first quartile, Q1, is 8, the median is 10, and the third quartile, Q3, is 12.5. For the new drug, the times are generally lower, ranging from 7 seconds to 12 seconds. Its Q1 is 8, its median is 9, and its Q3 is 10. Now we can draw the parallel box plot. We'll create a single number line to represent time. Above it, we'll draw the box plot for the new drug using its 5-number summary. Below it, we'll draw the box plot for the old drug. Notice how they are aligned. This single visual allows for direct comparisons. Let's analyze it to answer the hospital's questions. Which drug acts faster and which is more predictable? First, let's compare the center, which we can do using the median. The median for the old drug is 10 seconds, while for the new drug it's 9 seconds. This means 50% of patients on the new drug became unconscious in 9 seconds or less, compared to 10 seconds for the old drug. Therefore, the new drug is generally a little faster. Next, let's compare the spread of the data, which tells us about predictability. A smaller spread means more predictable outcomes. We can look at the range and the interquartile range. For the new drug, the range is 5 seconds and the IQR is 2 seconds. For the old drug, the range is 16 seconds and the IQR is 4.5 seconds. Both measures of spread are significantly smaller for the new drug. This indicates that the new drug's effects are less variable and more predictable. The hospital now has clear, data-driven answers. We've covered box plots, a visual summary of a single data set. What if our data is grouped, or we want to find specific values like quartiles from a frequency table? For that, we use cumulative frequency graphs. By the end of this section, you will be able to construct and interpret cumulative frequency graphs to estimate the median, quartiles, and other percentiles for grouped data. Let's use the marathon data from your notes to illustrate the process. The first step is to add a cumulative frequency column to our frequency table. This column shows a running total of the frequencies. For example, for the interval 146 to 148, the frequency is 8, so the cumulative frequency is 8. For the next interval, 148 to 150, we add its frequency of 3 to the previous total of 8, getting 11. We continue this process until we reach the end, where the final cumulative frequency, 69, represents the total number of runners. Next, we plot this data to create our cumulative frequency graph. We plot the cumulative frequency against the upper class boundary of each interval. For instance, for the first interval, we plot the point, 148, 8. For the second, 150s, 11, and so on, until we reach 176, A. Then we join these points with a smooth curve. This curve gives a running total of the number of runners who finished in less than a given time. Now for interpretation. The graph allows us to find percentiles. A percentile is a score below which a certain percentage of the data lies. The median is the 50th percentile, meaning 50% of runners finished in less than that time. We have 69 runners in total, so we need to find the time corresponding to a cumulative frequency of 50% of 69, which is 34.5. We locate 34.5 on the cumulative frequency axis, draw a line across to our curve, and then a line down to the time axis. We can estimate the median finishing time to be approximately 154.5 minutes. We can answer other questions too. For example, let's find the time taken by a competitor who finished in the top 20%. Being in the top 20% means they finished faster than the bottom 80%. So we are looking for the 80th percentile. We calculate 80% of the total runners. 0.8 times 69 is 55.2. Locating 55.2 on the cumulative frequency axis, drawing across to the curve and down, we can estimate that a time of approximately 159.5 minutes corresponds to the 80th percentile. This means 80% of runners took 159.5 minutes or less. So, the top 20% of competitors finished in less than about 159.5 minutes. You now have the skills to analyze and interpret data presented in frequency tables using cumulative frequency graphs. We've now covered all the main topics. Let's practice with some IB-style questions. This will test your understanding of how to apply these statistical tools. We'll work through 5 questions. Feel free to pause the video after I present each question to try solving it on your own before watching the solution. Question 1 asks you to find the median, range, and interquartile range from a given box plot. Let's find the solution. The median is the line inside the box, which is at 35. The range is the maximum minus the minimum. 75 minus 10 equals 65. The interquartile range is Q3 minus Q1, 50 minus 25 equals 25. Question 2 asks for the interquartile range from a frequency table and to calculate the outlier boundaries. First, the data is already ordered. We have 14 values. The median is between the 7th and 8th, which are both 6. So the median is 6. Q1 is the median of the lower half, which is the 4th value. 5. Q3 CI is the median of the upper half, which is the 11th value. 8. The IQR is Q3 minus Q1, so 8 minus 5 equals 3. The outlier boundaries are upper boundary equals 8 plus 1.5 times 3, which is 12.5. Lower boundary equals 5 minus 1.5 times 3, which is 0.5. Question 3 presents a parallel box plot and asks you to make a comparison. Let's compare. Class 2 has a higher median score, 70%, than Class 1 at 1%, indicating they generally performed better. The IQR for Class 1 is 18 and for Class 2 is 15. Since Class 2 has a smaller IQR, their scores are less varied and more consistent. We're nearing the end of our lesson on descriptive statistics. Before we continue with the final 2 practice questions, I want to briefly mention that if you're finding these topics challenging or you want to improve your grades further, DAR Tutors offers expert personalized tuition in IB, A-Level, and IGCSE. Our tutors can provide the one-on-one support you need to build confidence and achieve academic excellence. Visit our website or contact us directly to learn more about our online and home tuition services. All right, let's finish up with our final 2 practice questions. Question 4 asks you to estimate the median and interquartile range from a given cumulative frequency graph. To find the median, we need the cumulative frequency for the 50th percentile. The total cumulative frequency is 80, so 50% of 80 is 50. Reading from a cumulative frequency of 40 on the graph, the median time is approximately 30.5 minutes. For the interquartile range, we find the first quartile, which is the 25th percentile, and the third quartile, which is the 75th percentile. 25% of 80 is 20, which gives the first quartile as 27 minutes. 75% of 80 is 60, which gives the third quartile as 32 minutes. The interquartile range is the third quartile minus the first quartile, so 32 minus 27 equals 5 minutes. Our final question involves calculating the percentage of students who received an award based on a score threshold from a parallel box plot. In Class 1, the upper quartile, Q3, is at 70%. This means 75% of the class scored 70% or less, and therefore 25% of the class scored 70% or more. In Class 2, the median Q2 is at 70%. This means 50% of Class 2 scored 70% or more. Therefore, a greater percentage of students in Class 2 received an award. Let's summarize what we've learned today. We started with box and whisker diagrams, which are visual summaries of the 5-number summary. We saw how their shape can tell us about the skewness of a distribution. We learned a formal mathematical test to identify and plot outliers, which helps us handle extreme data points rigorously. Parallel box plots were introduced as a way to visually compare 2 or more data sets, allowing for quick insights into their centers and spreads. And finally, we covered cumulative frequency graphs, a key tool for grouped data that enables us to estimate medians, quartiles, and percentiles. These statistical tools are fundamental for your IB Maths AI/HL course. Mastering them will enable you to describe, analyze, and interpret real-world data effectively. Thank you for watching. Remember, for more in-depth explanations and personalized practice, you can always contact DAR Tutors for online and home tuition. We're here to help you succeed.